Thank you, Madhuri. And thanks the organizer, Sai Kriti, Vandana, and all everybody behind the curtain. And thanks for giving me the opportunity to present my work here in this forum. So the thing which I'll be talking about, just pardon me if it is below the level, but I have tried to, I thought that most of the students from the GITAM University will be here. So that was the reason for presenting my talk like this. So it is mainly based on the imaging technique which we have been using, or the equipment which I have built over the past 11 years, which I have spent in this beautiful institute. In this institute, which is almost 15 years old. So it was, I mean, when it started, there were only, in 2016 we moved this to permanent campus. There were only 3 buildings then, which you see here. These were the only 3 buildings which we had. Now if you come to the campus, it is actually transformed into a really big campus now. So please come and visit it. It's very beautiful campus. So in this campus, when I started, there was nothing. Even buildings were not there. So the things which we had, not even the funds. So the things which we had was M. Krishnamurthy, who had, so he had donated few of the chambers, and with those chambers and the steel bars which were lying in the lab. So from there we started making some spectrometer, and this is what the output of the steel which was lying in the lab, and we have made really a beautiful spectrometer out of that, and that is what actually give us really beautiful results, which you see in the slide. So these are just few glimpses of the part of work which we have done. And it is quite a lot. I mean, sorry, I don't want to advertise on this one, but yeah, basically we started from nothing, and yeah, it was really, I feel proud that with me, with the help of my team at IITH, we are able to do lot of science, and along with the application imaging as well, which you will see eventually. So these two anyway I will be presenting today. This one I will not be, but we have study small molecules, I mean from atom to the molecule, little bit complex, and we have actually moved towards imaging the tissues and all. So this is how we have evolved over last 11 years. So the whole talk I will be presenting from a diatomic molecule, where we will be trying to freeze a small molecule, small diatomic molecular ion, singly charged molecular ion in this space. This will be my first part of the talk. In the same scenario, if I make I mean, it can mimic the diatomic molecule. It is, you can see that this is a CS3I molecule. It is more like a diatomic molecule because there are 2 candidates, 2 big bulky atoms in there. So you can mimic that, and then if you little bit tweak the laser parameters, we can have highly charged ions as well. So this will be the second part of my talk, and in third part of my talk I will take you to the application side, where we are trying to make one device where it will be an automated device, where the robot can actually do the IV. The intravenous therapy will be done by a robotic arm, and that we will move towards the end. So so this 3 is overall, I have put in one umbrella of imaging. So how are we? So in the first part, so to do the ions, to see something which you cannot see, so that actually is basically we have made, that is called the ion spectrometer, where you ionize the system, you make the ions, and you push them by the electric field. The same 11th, 12th physics one has to apply. You push the ion towards the detector, and you push it in such a fashion that certain kinetic energy will be focused at one position, or on one circle. So this is the idea is not very new. It was actually discovered by Epping and Parker, but we have actually provided a very good recipe to do to study the kinetic energy without actually using dependent on the photon sources, which we don't have in the lab right now. So this whole system is basically 3 electrode system. You have a pusher plate which pushes the ion, then there is a puller plate which attracts the ion, and then you just put it on the detector. So lower energy ions will be focused at the center, higher energy will be focused at the periphery. So they will make like the onion. So you peel out the onion, the outer one is basically having the ion, more energy. You peel out the onion and coat deeper and deeper. The inner circle, when you reach, that is the lowest energy ion which you actually are detecting, and that gives you the history from where these ions have come from. And history means the energy levels they are born with. Okay, so every atom has, there are discrete energy levels. So is true for molecules as well. Okay, so that is what we try to study. So this instrument, so we have, how do you really probe it? So this is the imaging instrument. You probe it with the photon. You can use any source. Basically, if I have to see inside the atom, I have to inside. Let's say I have to see inside the apple whether the seed is small or big. I have to cut it, right? So likewise here we have to cut the atom, cut the atom, and we can cut it by any source. So here what we are using is the ultra short laser pulses. So here the parameters for these laser pulses are like, you have the energy is something about 30 microjoule. We have 25 femtosecond pulse duration. I mean, it survives for 25 femtosecond. The wavelength is somewhere around 800 nanometer. These are the peak intensities, and here we can actually change the intensity, and also we can change the wavelength by just doubling crystal. So when you combine this laser source and our spectrometer, this is the laser source and the spectrometer, it actually, what you get in your hand is basically, this is the laser pulse which comes in. Sorry, this is not visible here, but there are 3 electrode system. So there is one electrode here, then there is another electrode here, then there is a laser focusing here, and then they are pushed on the detector. So the thing which we get is the time of flight and the position image. This is how it would look like, and this is what I was talking about, has the onion slices. So this is the oxygen molecule. So what the kind of structure we see, if we just take a slice of this time of flight, the middle slice, the resolution in the position spectrum is even more better. What you see here is quite, so there are 4 lobes here, and it's not very good resolution at the lower energy. So we are not looking into this one, but the ones which are having the higher energy, we can actually look into it. So we can, so we need to know that what is the energy, and we can actually calibrate the energy. So this is by, as I told you, that lower energy will be hitting at the center, higher energy will be hitting at the periphery. So I can know the energy. So this is how I can generate the energy equation. This is the calibrated energy equation, and I can know the energy of the ion. So once I have the energy of the ion, I can start understanding the ion. So this is how the energy spectrum of the oxygen ion would look like. Okay, so now if you look at the molecule, so in a molecule, what is basically the orbitals have a different shape. So like in atom, you might have heard of s orbital, p orbital, d orbital, right? So s orbital have the spherical symmetry, then p orbital has a pi kind of a structure, then you come to the d orbital, it has 4 lobes like kind of structure, right? Similarly, in the molecule, this happens, right? So the highest occupied molecular orbital will be having this kind of shape. This green, this blue which you see, and this red which you see is the electron cloud. Okay, and the solid ones which you see are basically the nuclei of the two atoms. This is oxygen, this is oxygen. Okay. So when my light, so this light is linearly polarized. Linearly polarized means there is an electric field which is oscillating only in one direction. Okay, and this electric field can only, so when this electric field has this is the nuclear axis. When the direction of this electric field is about 40 degrees, So electron have the probability of getting aligned in this one, and then that can actually skip out of the molecule, right? So this, if the molecule is aligned in this way, so electron will go out, and then the ions which will be flying apart will be detected as a 4-lobe here. So ions can come here, can come here, can come here, and can come here. So this is what we see here. So we can actually back calculate what are the energies actually they are coming from, and we can essentially so this is the highest occupied or orbital of the molecular oxygen, which is pi symmetry. So this is not, this is actually quite intuitive that the ions will be flying in the at an angle of 40 degrees, right? So this was already predicted by ADK, which is these are the 3 scientists who had actually tried to calculate the tunneling ionization and calculated the symmetry of the ions, the way they will be coming out. So when we increase, so what is happening here, when we increase the intensity with 800 nanometer laser pulse, what we see that these lobes try to actually pull together. So they try to they try to come together. This is the polarization direction. You see that as we are increasing the intensity, so the lobes are coming together and it becomes more of isotropic. In this direction, the ions are hitting this at this point and this point, right? So they are not there. You don't see any 4 lobes here. But so here we say that molecule is basically, you are applying the electric field, the ion is being pushed like that, right? But the moment you change the 800 nanometer, this is not happening. You are changing the electric field, this is not happening. Why molecule is not rotating? So what is happening at this point? So 800 is able to rotate and 400 is not able to rotate. So now you have to go little deeper and tag that where the molecular ion has come from. So now we need to really look into the thing what is happening here. So when we looked into, this is what we had, and this contains all the information. So the low energy ones, as I told, are not very well resolved. The one which is resolved was this high energy one. So when we looked into it, so what we saw that these are the, energetically allowed state is that, so the electron gets ionized and the nuclear wave packet lie in this state and eventually it evolves. They are actually going far away from each other. So it is getting into the dissociative state. And the way it evolves is it's going from quartet pi Ungerad state to singly dressed quartet sigma Gerard state to doubly dressed quartet sigma Ungerad state. So these are the 3 states which are actually being participated for this transition, for this particular case. So when we try to understand that why molecule has to rotate, so we need to bring into these states in the electric field, and we wrote the equation, Lagrange equation. So there is a polarizability of the states which are lying in here. So this is the electric field direction of the laser pulse, and this is how the molecular ion would have been oriented, and it can orient in any of the direction. Okay. The ones which are around 40 degrees will have a higher chances of getting ionized. So so this is the electric field direction. So you see that there is a polarizability alpha parallel and alpha perpendicular. Alpha parallel is the polarizability along the electric field, and alpha perpendicular is perpendicular to this one. So this delta alpha here will decide whether this molecule will rotate or anti-rotate, right? So now when we looked into it for 800 case, what we saw that the whole pulse actually stays for only 5 femtosecond. Within that 25 femtosecond, the molecule actually is basically staying in quartet pi Ungerad state. Okay, so when we calculated the polarizability of it, it is basically delta alpha, which when we calculated, it is positive. So this means the molecule actually is rotating. But at 400, what we see that this is at this particular this is almost of a 35 femtosecond pulse. So molecule goes in this quartet pi-on-Garade state, and there is substantial intensity over here as well of the light, which actually where this quartet sigma on-Garade state also is there. When we calculated the polarizability of it, this is basically the negative. So the electric field of the laser is trying to align, but the negative polarizability is trying to anti-align. It is like कि oxygen, so there is a dialogue in the movie, one of the movies कि उसको liquid oxygen में डाल दो, liquid उससे जीने नहीं देगा और oxygen उससे मरने नहीं देगा. Same thing है, electric field is trying to align it, but this delta alpha is not trying to, it is trying to anti-align it. So it appears frozen, and that is what is happening in our case.
I just want to clarify one thing.
Yeah.
You use the word Garade state and un-Garade state. That's odd and even state.
Yes, those are odd.
Oh, okay.
Those are odd and even.
Yeah, no, you use the term Garade and un-Garade.
Because those are German scientists. So
German terms.
German terms. Yeah.
That's what
Yeah,
I
odd
was
and
confused about that.
I think maybe we'll take questions at the end.
No,
full public
she was
lecture.
on.
Yeah, it's a full
Garade
public
and
lecture, so it may be easier if we take questions at the end.
So now, so this is so basically at 400 the molecular ion appears frozen, and we call this as the transient negative polarizability. Basically, it is frustrating the alignment, so it is not allowing it to align it. So the more details you will find in this paper, which was published in 2020, somewhere around that. Now coming to the next experiment, where we are keeping almost same. It's a laser is same, so parameters will also be the same. The only thing is that whatever is in our hand we can change. So there, what we try to change is the pulse duration, and the intensities were kept constant there, and the only thing which we changed there was the pulse duration. We tried to stretch the pulse as much as possible. So the range which we actually changed it to from 25 to 1500 femtosecond. Now same spectrometer, velocity mapping spectrometer was there, and we put the light there and then allowed the CS3I ion interact with the laser pulses. And what we saw at the two extremes, so we took many data in the middle, but I just showed the extremes here. So at the 25 femtosecond, what you see is very few ions, and those are all of them are basically singly charged ions. But at 1500 femtosecond, we start to see multiply charged ions. You see that this is CS3I plus ion, this is a parent ion. We have I plus ion, then we have I a double plus ion, then we have CS3 fragments. It's basically CH plus, C plus, all fragments are there. So there are lots of, intensity is same. So what is happening there? So if we can crank up the intensity, it is quite understood that if you crank up the intensity, there are lots of photons available to ionize the system. But it is not, but at lower intensity, what is actually happening? So we try to understand further. So this is just the zoomed in view. So you have this here at 1500 femtosecond, we have quite a lot of ions. Again, more fragments here at 25 femtosecond and 1500 femtosecond. We see that there is a I double plus ion formation as well. Okay. So and we start to see that what is it actually increasing. So we just took the counts, and basically it is continuously increasing, and then after maybe 600 femtoseconds it tries to stabilize. So now we look into the energy levels, and that those energy levels actually come from velocity map imaging technique. And when we did that, so this is where I just took the two ions here, and these are basically the ones which are Coulomb exploding, and those ions are coming together. So like if CH3I double plus, if there is you remove the two electrons, so that CS3I double plus can break up into CS3 plus and I plus. It can also break up into CS3 neutral and I double plus. So what I am looking at is the one which is basically equally shared, and then maybe we can actually extrapolate the same thing for the highly charged ions and say that this is the reason why we see the multiply charged ions there, or highly charged states where we see that. So when we looked into it, so this is how the electrons are arranged in CS3I molecule, and this is the X tilde state where we have the highest occupied molecular orbital is basically E2E state, which looks like something like that. Okay, so this is the nuclear axis. You can say that this is the internuclear axis, and this is the 2E state where this is how the electrons are arranged, and in the 3A state the electrons are arranged something like that, and this is the direction of polarization. Okay, so this one, if the electrons are arranged, if somehow you see that electrons are aligned along the direction of polarization, we can actually kick out the more and more electrons. But this is deep seated inside. It is, I mean, this is the valence shell. This is, however, one shell below. This is HOMO -1, highest occupied molecular orbital -1. Okay, so this is the highest occupied orbital. So where you can actually kick out the electron. So both states are actually probable in this intensity which I am talking about, but we have that singly charged electron. So, but what is happening? What is actually leading to the multiply charged state? So basically, when we did the calculation and we took out we removed the first electron, and this whole CS3I plus ion, it tries to evolve over the time. So when it evolves, they are actually getting separated apart, so that this distance is increasing. Okay, so when distance increases, basically when the distance is increasing, so those two states which I was talking about in the previous slide here, these two states, they actually, as this R is increasing, these two states are coming closer, and you can couple it with one photon. When you are able to couple exactly with the one photon, we call it as a resonance process. Okay, so so basically for the longer duration, what is happening, that for a shorter duration we are not able to reach to this point. For the longer duration we are able to reach to this point where we still have the photons to couple between these two states, and when the electron actually can couple from 3A to 2E or 2E to 3A, so which is aligned along the polarization direction, and we can eject the electron out, and that is the reason why we are able to see that the higher charge states for a bigger pulse duration. So as a summary for the whole fundamental science result is basically we did oxygen and the CS3I molecule. For oxygen molecule, we tried to we changed color from 800 to 400, and what we saw that because of the transient polarizability, the molecular